In general, if we're working with function y equals f of x at x equals to a, and we want to approximate, so we want to approximate it using polynomial approximation Pn of x. What we'll require is value of function to be the same as value of polynomial at x equals a, that we will have the same derivative function and polynomial at a, we will have the same second derivative at x equals to a, and so on, all the way up to the nth derivative, and we'll require nth derivative at a of function to be the same as nth derivative of polynomial at a. So it's the general situation. Now let's investigate what will be happening when a equals to 0. So when a equals to 0, so our polynomial is going to look like, nth degree polynomial is going to look like c0 plus c1x plus c2x squared plus and so on, plus cn x to n. Then f of 0 equals to Pn of 0, and if we substitute x equals to 0 here, we're going to get c0. So we conclude that c0 equals to f of 0. Now we're going to use the second line to figure out what's happening with the first derivative. So to do that, we need to find what will be the derivative of polynomial. Derivative of polynomial will become c1 plus 2c2x plus and so on, all the way to n cn x to n minus 1. So we conclude that f prime of 0 equals to p prime of derivative of polynomial, and substituting 0 for x, we're going to get c1. So we conclude c1 equals to f prime of 0. Now we're going to use the third line, that second derivative of function should be equal to the second derivative of polynomial when x equals to 0 in our case. So we're going to need to find the second derivative of function. So we're taking derivative of that expression, so we're going to get 2c2 plus and so on, plus n times n minus 1 cn x to n minus 2. Substituting 0 for x, we're going to get second derivative at 0 is going to be equal to just 2c2, and it's supposed to be equal to the second derivative function at 0, and we conclude that c2 equals to second derivative at 0 divided by 2. So far we found that c0 equals f of 0, c1 equals f prime of 0, c2 equals second derivative at 0 over 2, and if we'll keep on finding, then we find that c3 equals the third derivative divided by 2 times 3, or 1 times 3, and c4 we're going to find it's a fourth derivative at 0 divided by 1, 2, 3, and 4, and in general we can find that the ck equals the kth derivative at 0 divided by k factorial. So what we conclude is we can write that as a formula that Pnx is nth degree polynomial approximation to y equals f of x at a equals to 0. If we're looking for Pn, which is nth degree polynomial approximation to function at a equals to 0, then we can get a formula that Pn of x equals to f of 0 plus f prime of 0 over 1 factorial times x plus second derivative at 0 over 2 factorial times x squared plus and so on all the way to the nth derivative of function at 0 over n factorial times x to n. Now, if we want to find p polynomial approximation, to y equals f of x, now at x equals to a, and x equals to a is not necessarily equal to 0, then essentially it's going to be the same formula as we have before. The only thing that's going to be happening is we have to shift by a, so we need to shift from 0 to x equals to a, so our formula is going to be, looking at this case, so instead of having f of 0 we're going to write f of a. Instead of writing f prime of 0, derivative at 0 will say derivative at a over 1 factorial, and because we're doing shift, instead of x we're going to have x minus a. Same happening with second derivative a over 2 factorial x minus a squared plus all the way up to nth derivative at a over n factorial x minus a to n. Of course, we're assuming here that our function will have nth derivative at a. So let's run an example. Find Pn nth degree polynomial approximation. Often it also will be called nth degree Taylor polynomial. To function e to the x at x equals to 1. The good thing about function e to the x, its derivative is always e to x, so value of derivative at 1 is going to be always e. So we are ready to use our formula which we derived earlier. So we're going to get nth degree polynomial approximation to e to the x at x equals a is going to be e plus e over 1 factorial x minus 1 plus e, which is our derivative, over 2 factorial x minus 1 squared plus and so on way to e n factorial x minus 1 to n. And that's going to be our answer for this problem. Next question we want to discuss: how accurate is polynomial approximation? So if we have function f of x and we approximate function by nth polynomial, nth Taylor polynomial, and we have some remainder, so here Pn is Taylor polynomial, then our remainder or error is equal to f of x minus Pn of x. So we want to make the following statement. If we want to find our error when x equals to b, then it's going to be less than f, and function of f raised function n plus first derivative function at z divided by n plus 1 factorial times b minus a to n plus first, an absolute value here. And here we assuming that Pn is Taylor polynomial at x equals to a. We assuming that our function has derivatives up to n plus 1, and z is between a and b. So the situation looks something like that. So we have some point A somewhere here, we have B somewhere here, and somewhere between them we can find Z, so that our remainder will be less than that. Usually, if we can get good handle on the n plus first derivative of a function, they can then say how big our error is going to be.